Right. So we continue with now video lecture 25, and what we realized from the last lecture is even though your rock may have the same minerals, say you have two rocks have the same minerals, but their fluid compositions are different, then if their two minerals becomes unstable, then the temperature at which they become unstable is not the same. But this also, it is understandable that the reaction involves fluid. That's the first and foremost thing that you should remember. That even if two rocks have the same minerals, it does not automatically mean that they're formed at the same temperature, because the fluid compositions may be different. And if the two minerals, A plus B, produces another mineral involving a fluid, then it would also depend on the composition of the fluid. That's a cardinal point that you should remember. The other cardinal point that you should remember is two rocks having different mineralogies, but have the same mineral composition, same fluid composition. The reaction would start at the same temperature, pressure conditions. And you can have all combinations of this. Now we go, after having understood this, we go into the next step. Now here, say for example, you have dolomite. If you go up temperature from dolomite, then you can see here that this reaction operates. I will erase this. This reaction operates. Reaction 1, let's say we have the question of reaction 1, where you have 5 dolomite plus 8 quartz plus 7 CO2, quartz plus H2O. This reacts to produce tremolite plus 3 calcite plus 7 CO2. Now that's important. The dolomite and the quartz reacts in the proportion 7:8. 5:8. Means what? The dolomite mole proportion of dolomite mole percentage is equal to 5 divided by 8 plus 5 is equal to 5 by 13, which is roughly equal to 40%. 40%. It would react in the ratio 5:8. That means nearly 40% dolomite and 60% quartz would react in the rock, irrespective of what was the proportion of dolomite and quartz in the rock. Irrespective of the proportion of dolomite and quartz initially in the rock. This is very, very crucial to understand. I will remind you of another diagram which involves the same thing. I think you have studied it, but I don't know whether this has been ever told. Say, for example, I have this famous diagram. You know, it's a very famous diagram where you have A, B, weight percent, temperature, melt, A plus melt, B plus melt, and A plus B. Simple eutectic diagram of igneous metal. I don't know ever whether you were taught what happens during melting. People normally talk of equilibrium crystallization. But when we talk of equilibrium melting, what happens is more compelling. It's more tricky. And that is very important. And that's where you will find the similarity. Say, for example, let's say the rock has this composition. The rock has this composition means, say, roughly A80, B20. Or maybe there is another composition here, which is A20, B80. Right? Let's say there are rock 1 and rock 2. And they have this composition. That means the mineralogy of pure A and pure B, just like we have dolomite and quartz, is A80, B20, pure A, 80, pure B20, or pure A20, B80. But this point here has, say, A75, B25. Now, if you take this rock, if you take rock R1 and heat the rock, and it reaches this temperature, which is called the temperature of the eutectic, then the rock will melt. The rock will melt. Similarly, if you have R2 and if you increase the temperature of the rock will melt at the eutectic, yes, but it will melt with A75 and B25. 75% of A and 25% of B. In that proportion, A and B will melt. But the initial rock composition are very different. It is a very, very similar situation. So whether you take A80, B20 rock, or you take A20, B80 rock, and when you heat the rock, when it reaches the eutectic temperature, the rock will melt. But the proportion of A and B undergoing equilibrium melting would occur with A75, B20. It will not be in the ratio as they are present in the rock. It never happens. This is what is very important to note. So if you have also, I won't go into the details, this is not an igneous metrology class. If you have a rock R3 which has the same composition as the eutectic, if you take a rock where A75 and B25 minerals undergo melting, A and B will melt in the proportion it is present in the rock. Why? Because that's the same proportion in which eutectic melting occurs. And both A and B will exhaust simultaneously and your melt will move in this direction. Otherwise, for rock R1, the L will melt in this direction, and for rock R2, the melt will move in this direction. But if the rock has A75 and B25, the same as the eutectic composition, then both A and B are present in the ratio 75:25, and they will melt in the proportion 75:25, and both will get exhausted at the same time. I don't want to go into partial melting because I don't think there's an igneous metrology class, but this diagram can be taught for at least 3 classes on equilibrium melting. Forget crystallization, it's easy. Melting is more complex. Melting has similarity with metamorphism. So in here, whether your rock contains dolomite 90, quartz 10, or dolomite 10, quartz 20, it doesn't matter. If dolomite and quartz are temperature, dolomite and quartz react to produce tremolite and calcite, then dolomite and quartz will melt in the proportion nearly 40:60. Nearly 40:60, irrespective of the abundance of the mineral in the initial rock. It is very, very crucial to understand this. But if you have a rock where dolomite and quartz are in the proportion of dolomite 40 and quartz 60, if the initial ratio of dolomite and quartz is 40:60, the dolomite and quartz will react in the proportion 40:60, and both will be exhausted at the same time. Just like equilibrium melting in a binary eutectic. Actually, it's not binary eutectic, it's the formula for melting in all ternary, quaternary systems. It doesn't matter. Theory doesn't change. So, this is very crucial. Dolomite in the ratio 40:60 quartz will react to produce tremolite and calcite in the ratio 1:3, not any other ratio. 1:3. 1:3. It will react in the ratio 1:3. And so you will have from the assemblage dolomite quartz. You will have the assemblage at points below this on this side. You will have dolomite, quartz, tremolite, calcite, in which dolomite will be consumed, quartz will be consumed, tremolite will be produced, calcite will be produced. See here, H2O will be consumed, CO2 will be liberated. There you go. All your reactants will go down. So dolomite proportion will go down, quartz proportion will go down in the proportion 40:60 or 5:8. H2O also will go down because H2O is being consumed. What will be produced? Tremolite and calcite in the ratio 1:3, and CO2 will be produced. So what will happen to the fluid? In the fluid there was H2O and CO2. H2O is being consumed. Consumed to do what? To produce tremolite, which contains OH2 radical. So OH will be held up within tremolite. So H2O will be reduced and CO2 will be produced. So say for example you have a rock here, dolomite and quartz. It starts to react here. So what will happen once the reaction starts? At this point the reaction will move in this direction. Why? Because in this direction CO2 increases. So the fluid which was in equilibrium with the rock, in which CO2 will increase, and there is only one way by which it will increase: this direction, no other direction. So if you have dolomite and quartz reacting in H2CO2 fluid, H2 will be consumed, CO2 will be produced, and so will be tremolite and calcite in the ratio 1:3. So you will have this assemblage. From dolomite quartz, you will have this assemblage. Dolomite, quartz, tremolite, calcite, H2O, CO2. This is of course a part of the fluid phase. From this, two things will happen. From this, several things will happen. Either you will have the assemblage dolomite, tremolite, calcite, or you will have the assemblage quartz, tremolite, calcite, or you will have the assemblage tremolite, calcite. There will be three things that is possible. One is here quartz is consumed. Here dolomite is consumed. Here both quartz and dolomite are consumed. Now you can look at this. If you have large proportion of dolomite, then quartz will be consumed. You see, 8:5. So quartz will be consumed earlier. So this is typical for, this assemblage is typical for siliceous dolomite. This is typical of siliceous dolomite. This is typical of dolomitic quartzite. And this is typical, the third one is typical, if dolomite 40 quartz 60. For this particular rock, tremolite plus calcite will be the only phase, where dolomite and quartz was in the same proportion as in the stoichiometry of the reaction, dolomite plus quartz. So this is three things that might happen. After you start with dolomite plus quartz, you will have dolomite, quartz, tremolite, calcite, and then you will be passing through this. And now you see, very interesting here, that you will have dolomite, tremolite, calcite, quartz, tremolite, calcite, and tremolite, calcite. Do you understand? It is very important to conceive this. Now you see here, as you go up pressure, as you go high temperature, and if quartz, dolomite, if quartz is consumed, then one phase is less, so the variance has to increase. Here, one phase is less, so the variance has to increase. Here, two phases are less, so variance has to increase. So what will happen? The rock system will not lie on this reaction line. So it will start, it will leave the reaction line and go into a bivariant space. It will go into a bivariant space. So you started with dolomite quartz and you have tremolite, calcite, quartz. Now you see here something interesting. If you have dolomite, if quartz is consumed, it's siliceous dolomite. Have a look at this, very simply. If you have siliceous dolomite, then you will have dolomite, tremolite, calcite as the product. Now you see here, as you move from the univariant, because the number of phases is decreasing, so the variance will keep increasing. So you will move up line, because you cannot be in the univariant line. So what you will do is, you will reach here. But what is the minerals here? Tremolite, calcite, quartz. But quartz is not there. So this reaction, although drawn here, will be overstepped. Because you don't have the reactants. Because you do not have the reactants. What is the thing that you don't have? You don't have quartz. So this reaction involves tremolite, calcite, quartz. But you don't have quartz in this assembly. So this reaction looks nice, but the reaction will be overstepped. Because one of the reactant phases of this reaction isn't there at all. Now let's look what happens. Here, if dolomite is consumed, as in dolomite, quartz, dolomitic quartzite, then you will have quartz, tremolite, calcite. Now you see, here you have trebolite, calcite, quartz reacting in the ratio 1:3:2, and so this reaction will operate. It will not, this reaction will not be overstepped. But look at this. If you have trebolite calcite, that means quartz dolomite is consumed, because they were in the proportion in which dolomite and quartz reacted. So what will happen is when the system moves from the univariant to the bivariant field, there is no quartz. So this reaction again will be overstepped. So for this case and this case, this case and this case, that means no quartz, this reaction will be overstepped. That means temperature will rise, but this reaction will not operate. What controlled this? What controlled this? What controlled this? That in these two cases the reaction is overstepped, but in this case only the reaction will occur. What controlled it? The bulk composition of the rock. The bulk composition of the rock controlled it. So your appearance of a mineralogy, stabilization of a mineral, would be a function of the bulk composition of the rock. That means the initial mineralogy of the rock. So two things can be shown. From the earlier thing I showed you how fluids manipulate the assemblages, and now I am telling you that how the bulk composition controls the appearance and disappearance of minerals, or the eventual configuration of minerals. So that is what happens. So from this you will have dolomite, trebolite, calcite, reaction overstepped, trebolite, calcite, reaction overstepped, quartz, trebolite, calcite, reaction operates. Reaction operates. Why do we go straight up? You can ask me, from the univariant line through the bivariant field. Why do we go up? Straight, because the temperature is rising, but there is no change in CO2 because no reaction is happening. So you are going up with the same fluid composition, but with increasing temperature. That's why your movement is along a vertical line. That is why your movement is on a vertical line. So now you can see here. So what will happen? Let's say we conceive of a point here, say, some temperature here, at this temperature. At this temperature, this will be stable, this is okay. At this temperature, this will be okay. But to what? Quartz from here, if I draw this, quartz, trebolite, calcite, you will have the situation where you have quartz, trebolite, calcite, dioxide. Because trebolite, calcite, quartz is there. From there, if the reaction happens, then you will add dioxide to the system. In this system, quartz will decrease, trebolite will decrease, calcite will decrease, dioxide will decrease, and I will tell you, effective CO2 in the rock will increase. Why? Because we will come to this question of H2CO2 a little later. Just give us this time, but I hope you have understood this. So if then quartz, trebolite, calcite, dioxide, if this reaction happens, then you can have several possibilities. You can have trebolite, calcite, dioxide, no quartz, or you can have quartz, calcite, dioxide, or you can have quartz, tremolite, dioxide. Depending upon which, according to which ratio there is, which one will be exhausted. Which one will be exhausted. And you can have the fourth thing, that somehow, some composition, some unique composition, your tremolite, calcite and quartz, when the reaction is reaching this line, tremolite, calcite and quartz in the ratio 1:3:2, in which case only dioxide will be there. and you will call it diopsidized. That is very, very important. So you see the wide variety of assemblages that have come up. Wide variety of assemblages that have come up at this temperature, at a hypothetical temperature. A wide variety of assemblages have appeared. You can have dolomite tremolite calcite, you can have tremolite calcite, you can have tremolite calcite dioxide, and then you will have quartz calcite dioxide, you will have quartz tremolite dioxide, or you might have just dioxide. And all of these variations are triggered by the variation in the bulk composition of the rock. And what controlled the bulk composition of the rock? The modal mineralogy of the initial rock. So the initial rock is something like your DNA which you were born. It has a huge influence on what you do later in your life. The bulk composition of the rock. That is a big, big determining factor of what minerals will be present during metamorphism. Just because they have different mineralogy does not mean that they have different temperature. No, it does not mean that. Different mineralogies does not mean they have formed at different temperatures. All these mineralogies are possible at this particular temperature. So once again, if you look at the metamorphic phases diagram, rocks formed or crystallized at the same pressure temperature condition, rocks formed or crystallized at the same pressure condition, the mineralogy of the rock formed at the same pressure temperature condition will be the same for the same bulk composition. Yes, that's right. Mineralogy of rocks formed at the same temperature will be the same for the same bulk rock composition. But mineralogy of the rock at the same pressure temperature will be different if the initial composition of the mineral, bulk composition of the rock is of course. This is where metamorphic phases principle comes in. Right? So I hope I have made things a little bit clear. Just before we move on to the other topics, I want to make an important point here. I will draw this I will attempt to draw this curve, reaction 3. I will just try to draw it. This is what will be the topology of the reaction. Tremolite, 3 calcite, quartz, 2 quartz. Tremolite, 3 calcite, 2 quartz. Dioxide, H2O, 3 CO2. This peak will be at 0.75. This we talked about when we were talking the topology of reactions, where you have A is equal to P plus MH2O plus NCO2. Remember that rock when XH2O by MnO2 will be in the ratio m by n I showed you? That is exactly the case. So the reaction, hump of the reaction should lie at XCO2 0.75 because 3 divided by 1, the coefficient of H2O plus 3, that is 0.75. So the peak or the hump of the line where the maxima of the curve should coincide with x is equal to 0.75. That will coincide with XCO2 is equal to 0.75. Now you see something that is important, and this is very, very crucial. As you move, you imagine this red line. You imagine this red line. Let's say you start your red line from here. Have you understood? After the reaction, remember, this reaction will operate if you have tremolite, calcite and quartz. This reaction will operate when you have tremolite, calcite and quartz. For other assemblages, it will be overstepped. This I discussed before. Right. For this reaction to produce dioxide, this reaction will happen only if the initial, if the preceding reactants are tremolite, calcite and quartz. You will produce dioxide in the ratio of XCO2. Here you can see XCO2 is in the ratio 0.75, where the maxima will be at XCO2 0.75. Now, if we are approaching this from this side, then this is our XCO2 value of the fluid before we reach this reaction. If, say for example, if your value of XCO2 in the fluid is 0.5 and we are going up following one of these lines, which are going through the bivariant fields because it has lost a phase. So if we are here, then for the rock before we reach, XCO2 is 0.5. But when we reach here, dioxide, when it is produced with a liquid where XCO2 is 0.75. Have you understood? H2 and CO2 are both produced. Correct? No problem. But H2 and CO2 are produced in the ratio 1:3. That means that XCO2 of the fluid is 0.75. So if this is so, just see here what happens. Just see here what happens. You're hitting the rock, so you're going up temperature. So XCO2 0.5 is there when you reach the reaction, but it produces XCO2 0.75. So what will happen? The system will move in this direction. Till this point. Have you understood? Tell me if you have understood. Of course, you can't tell me. I hope you understood. That you start with here on this line, where you have XCO2 0.75, and you reach this. When you reach this, you produce a fluid, XCO2 0.75. So 0.5 fluid was there before, and you're adding XCO2 0.75. So the fluid in equilibrium with the rock is becoming more and more carbonic rich. Have you understood? But the peak is at 0.75. Now you see what will happen. If this reaction goes on, then you can't go this way down. You see, this way down you can't go, because this is going down temperature, but you're heating the rock. So it's contradictory. So what happens if you start with the fluid of this composition and then you reach this reaction? The reaction will become carbonic up till here. The system cannot follow this path. It cannot follow. So this reaction will proceed till tremolite, calcite and quartz, one of the phases is lost. So long it will produce it. But as soon as one of these reactants is lost, the system will move up from this. We will, in this part, we will differ it. But it has to leave this line. Why? Because it has lost the phase. So the variance has to increase. But remember, the system cannot cross over. Now, let's go to the other extreme. Let's say we start with a rock here, corresponding to the red. We start with a rock with a CO2 value, say 0.8 or 9. Now you see what happens. It is very interesting. Now the rock, before it reaches here, had an CO2 value which is 0.8. 9. Okay? But when the reaction is operating, HCO2 is being produced with a ratio 0.75. So what are you doing? Although you are producing a carbon-rich fluid, but your initial rock had a higher carbonate, CO2. So if you add HCO to 0.75, then your earlier HCO to 0.85 is becoming less carbonic. Have you understood? It is becoming less carbonic because you started with a higher HCO2 value. So what will happen? The system will move in this direction. Again up temperature, progressive metamorphism, but it will move in this direction. Why? Because you started with a higher value of HCO2 in the rock, but you produced HCO2 at 0.75. Therefore, your rock became more hydrous. It's very contradictory that your HCO2 value of the rock is becoming more hydrous, meaning HCO2 is decreasing. Although you're producing a fluid with HCO2 0.75. Sounds almost like a love story with no meaning, but it's true. It's almost like a love story. It has very little wise words in it, but that's how it is. It's because it's strangled in logic. That if you start with a high HCO2 value and you encounter the reaction produces HCO2 0.75. So you're producing HCO2 0.75 in where there is already a fluid HCO2 0.8 or 0.9. So you're essentially fluxing the carbonic rich fluid by HCO2 0.5, which is more hydrous. Have you understood it? It's more hydrous. Numerically, it is more hydrous, although it's very highly carbonic, but not as carbonic higher than 0.8. It's less than that. So you're hydrating the fluid. So what will happen as you reach here, but then you can't go down because you're heating the rock progressive metamorphism. You can't go down temperature, and so this way you're going to go up. The same path that another rock took to reach here by becoming more carbonic, this path can be taken by this rock as well as from this path. I think I will give you 1 minute to think about it. You start with HCO to 0.5, add fluid HCO to 0.75, so your composition of the system moves towards higher CO2 value, but till HCO to 0.75. Greater than 0.75, there is a curve acting downwards. You can't go down temperature during progressive metamorphism. And then you have the counter case, where you have a rock that contained higher HCO2 value, and it reaches the reaction curve. And when the reaction happens, HCO2 is 0.75, which is lower than your inherited HCO2 already. So you're essentially fluxing your rock with less and less HCO2. So that is why you have to move both. They converge along the line. In both they produce dioxide. In both they produce H2O plus 3CO2. But in one case the trajectory is to the towards high temperature, towards high CO2, and another trajectory is away from the high CO2, eventually reaching the hump, the maxima, and then mutating the same path. So this is a very, very crucial thing to understand. So you can imagine now, having said this, it's I think important to now get a grasp of the whole thing. That eventual, here you see there is a complex problem. Here by this method, you're not changing the composition of the mineralogy of the rock, because tremolite, calcite, quartz in both ways in this ratio is reacting to produce H2O and CO2 in the ratio 1:3 and producing dioxide. So when you go this way or you go this way, you're producing dioxide and H2O, CO2 in the ratio 1:3. But you're following two completely different trajectories. In one, you're making your fluid more carbonic. In another way, you're making your fluid more hydrous. More carbonic from the H2O end, more hydrous from the CO2 end. And both of them end up right at the peak of this type of reaction, A is equal to B plus MH2 plus NCO2. This is what eventually happens. And that is very crucial. So what is being important to realize here, that the initial bulk composition of the rock, dolomite is to quartz ratio, and the initial composition of the fluid, H2CO2, both have a tremendous effect on what type of reactions will operate. What type of reactions will operate? What will be the eventual assemblage? These will be dictated by the bulk mineralogy of the rock as well as the fluid composition of the rock. This is very, very crucial to understand. Very crucial to understand. I hope I have made myself clear on this. Now, one last thing before I wind up for these classes. I will just erase these lines, create a little disturbance. Now, let's say we take these two rocks, but we assume the CO2 was high. So what happens, let's say we start with the CO2 something like this. That is more carbonic than what we had. More carbonic than what we had. So what happens once again with dolomite plus quartz? In the ratio 40:60 they react and they produce, tremolite is locked up, H2O is locked up in the tremolite as a H2 radical and CO2 is produced. So the fluid composition moves this way. And then we could reach this point. What is this point? This is called an invariant point. And this is called the invariant point of phosphorite. This. Why? Because what are the assemblages here you see? The assemblages are dolomite, quartz, tremolite, calcite, dioxide fluid. These are the phases. So 1, 2, 3, 4, 5, 6. So the phases P is equal to 6 and C is equal to 5. C is equal to 5. 1, 2, 3, 4, 5. So C is equal to 5. And so your variance F is equal to C minus P plus 2. And so you have 5 minus 6 plus 2. And that is 7 minus 6 is equal to 1. But you have an isobaric diagram. So this becomes 0. Right? So the actual variance is 1. But at isobaric conditions, the variance is 0. And what are the metamorphic variables? The metamorphic variables are pressure, temperature, XCO2 or XH2. These are the metamorphic variables. So you see here, your P is already known because you have taken isobaric diagram. And your variables are 1 point, then T and XCO2 are known. That means this point is isobaric invariant. Remember, it's not an invariant point in the strict sense of the term. It's isobaric invariant. But actually, it is an univariant. In a field where it is TXCO2P, that P is a variable, there its actual variance is 1. But for an isobaric section, P known, this is 0. Now this is given by I, and there is the phase missing from here among all the phases that we have taken is Fosterite. So this is called invariant point, Fosterite invariant point. But remember, when we say invariant point, it's isobaric invariant, not invariant. It's univariant if you take pressure as a variable. Right. Now, if you do this, if you have a composition here and reach this, what did you have initially? You had dolomite and you had quartz. And then through the reaction, you had dolomite, quartz, tremolite, calcite, from which you can have the reaction dolomite, tremolite, calcite. You can have quartz, tremolite, calcite. Or you could have tremolite, calcite. When you reach here, now you see, if you have quartz, tremolite, calcite, then you are going to move in this direction. You see here, this invariant point is in the high CO2 side of the hump of the reaction. This is what I was drawing with the blue pen a few minutes ago. So if you go up to here, and then if you have quartz, tremolite, calcite, then you move in this direction. Right? But if you have just tremolite and calcite, then you move in this path. This path will only be valid if you have dolomite and quartz, and somehow tremolite, calcite did not have. If you still have dolomite and quartz residual, I must say, of course, that your CO2, H2 is completely consumed, and you still have dolomite and quartz, then you will go on this side of the reaction. If you had dolomite and quartz, if you had tremolite and calcite, you will go up this reaction, and if you have quartz, tremolite, calcite, you will move in this direction. If you have dolomite, tremolite, calcite, then you can see what will happen. You will also follow this reaction. Why? Because tremolite and calcite react here. You don't need dolomite. So for tremolite, calcite and tremolite, calcite, dolomite, tremolite, calcite and tremolite, calcite both follow this. If you have quartz, tremolite, calcite, you follow this path. If you still have dolomite plus quartz existing, then you follow this path. So it's like you go out from the institute main gate. I don't know if you've seen the institute still away. because of the pandemic, I don't know. If you go out of the institute main gate, there is a goal around in front of the main gate of IIT. So there is a road that goes, if you're coming out of IIT, you go straight down the road, and there you first, one of our favorite halls when we were students was the girls' hostel. So it's right down your nose. On the left, you go to the campus, and on your right, you go out of the campus. So there are 3 roads. And depending on what is available, these are the 3 roads available. You want to meet your girlfriend, you go straight down. You want to go to meet your parents, go straight to the left. And if you want to go and leave your girlfriend and your parents, you go right out to the right. Yeah? So here it is. Your desire, whatever you have as a reactant, this is how it will work out. Everything is scientifically done. So this is what are the gamut of situations that exist in this part of the diagram. And this is very fundamental. This is extremely fundamental for you to understand that metamorphism is not geothermal barometry. This is garbage. Metamorphism is a much more complicated subject if you bring in fluids. And fluids, today more and more evidence is coming up that, okay, just before I do this, when I was discussing all this, one thing I did not tell you was that I was considering closed system metamorphism. That the fluid remained within the system. But the composition of the fluid and the mineralogy was continuously changing. The composition of the fluid and the mineralogy of the rock was continuously changing. Nothing went outside. Nothing at all went outside. So we were considering closed system metamorphism. This must be very clearly understood. We were talking of closed system metamorphism. Okay? These are sometimes called as internally, we will go into this in the next system, we call it internally buffered systems. So these are for this closed systems. And when you come to an invariant point, your existing mineralogy will tell you which path to go. And that's you the only possible path. Say, for example, dolomite, trebolite, calcite, both follow this path to reaction 5. Quartz, trebolite, calcite takes you to reaction 3. And if you have left dolomite or quartz by some way, you have to move to the right towards reaction 2 to make yourself more carbonic fluids. That's how it works. Okay, I think I will stop here. We will continue the discussion in the next class. Thank you.